Before starting this lecture, I should rectify a mistake that I made while discussing in the previous lecture. So in the previous lecture, I had drawn the magnetic field lines from the curved pole faces, suppose from this North Pole to the South Pole in terms of straight lines. Those were intersecting each other. So that was one mistake that I made. So one of the students from section B identified or raised this point that the magnetic field lines theoretically, or as we know, should not interact each other. So I didn't realize that phenomena while I was discussing this portion, that why the curved pole faces were used, while the reasoning was okay, but the way I had drawn the magnetic field lines or magnetic flux lines was not correct, because the point raised by the student, I later on reviewed the topic, and yes, the magnetic field lines should be separate. They should not intersect or interact with each other. So the way that I had drawn the magnetic field lines in the previous class in terms of straight lines, that is not right. So rather, I should redraw it in the general way as it is represented in terms of curved pole faces. So the magnetic field lines, let's say from the center, it would be in terms of a straight line from the North Pole to the South Pole. But along the curved pole faces, they will bend a little bit and then they will reach the South Pole. In this way, the magnetic field lines will be separate from each other. They will not intersect as they pass from one pole to another. Similarly, on the other side, we can also draw similar magnetic flux lines. So they will be separate field lines actually. But the thing that the curved pole faces, why they are used to ensure that the moving coil edge is facing the magnetic pole perpendicularly, so that the magnetic field line at an angle enters at right angle into the edge of the coil, so that the torque generated by the or experienced by the coil is maximum, and it stays uniform throughout the different angles of rotation. So whatever the angle of rotation is, the moving coil is directing towards the pole perpendicularly, because of the curved pole faces. So whatever the moment, according to the curvature of the poles, the moving coil will always be aligned along the radius of the curved pole face. So the magnetic flux lines are supposed to enter or cut the edge of the moving coil perpendicularly or almost perpendicularly, resulting in the maximum possible torque to be experienced by the moving coil. And throughout the entire range of deflection, the torque is supposed to remain almost uniform. So the uniform scale can be used in terms of measuring a particular quantity. Now, this PMMC meter structure that was discussed in the previous class in terms of detailed diagrams. Now, to simply represent them in electrical circuit, this sort of an symbol is often used, where the PMMC deflection mechanism is represented by this circular symbol along with a pointer, and along with this symbol RM and IM, they actually indicate the resistance of the moving mechanism or the internal coil mechanism. So Rm, it represents the resistance of the mechanism. And IM indicates the full-scale deflection current that can be carried by this particular coil arrangement. So the full-scale deflection current is also sometimes denoted by IFSD, full-scale deflection. So IM is the current required to give the full-scale deflection of the pointer, and Rn is the internal resistance of the coil arrangement. So later on in discussing DC ammeters or voltmeters, we are going to use this circuit representation of the PMMC deflection mechanism in order to indicate the presence of the PMMC arrangement. So now this PMMC meter movement mechanism can be used to form a DC ammeter. So in this case, as the basic DC ammeter circuit is shown over here, so this portion is actually indicating to the PMMC meter, and along with that a shunt resistance RSH is connected to use this arrangement in terms of measuring the values of electrical currents. Now normally the PMMC meter movement mechanisms are such that they can handle currents of very small range. Let's say the full scale deflection current IM, that is normally, let's say, in 1 milliampere range, and the internal resistance could be, let's say, 50 ohms. So if the shunt resistance is not connected, what will happen? Using this meter movement mechanism, it would not be possible to measure currents beyond 1 milliampere. So that would be the maximum range that could be measured without the shunt resistance. Now, using suitable values for the shunt resistance, the range of measurement can be increased. For example, let's say if this shunt branch is there, then a current up to the value of I can be measured using this arrangement, depending upon what is the value of RSH. So in that case, the current that is going to be passing through the shunt branch is I minus IM. So the PMMC meter will carry its maximum amount of current or maximum rated current, which is the full scale deflection current, and the rest of the portion is going to be bypassed through the shunt resistance so that the PMMC coil doesn't get damaged. So by choosing the suitable value of the shunt resistance, the range of measurement can be increased, let's say, from 1 milliampere to a higher level. So now for calculating RSH, now we can consider the voltage drop across the PMMC and the shunt resistance, because they are going to be equal, so we can easily equate them. And from here we can easily determine the shunt resistance. Now ISH, we can easily replace it as I minus IM, and later on if we further try to simplify this, it would become I by IM minus 1. So the value of Rm for a particular PMMC arrangement is supposed to be fixed. The value of Im is also supposed to be fixed. So what is the range of current that we want to measure? Let's say we want to measure 100 milliohms using a 1 milliampere PMMC. Then we can put the value of 100 milliohm, or we can determine this ratio, which would be actually 100. And later on, Later on, using this relation, we can easily determine what would be the shunt resistance required to achieve a maximum limit of 100 milliohms. And this ratio is often denoted by N, and this relation with RSH is represented in this format. So using different values of RSH, different ranges can be obtained. So let's say if we consider a multi-range emitter, so normally in different emitters we see that there are multiple ranges. We can change between one range to another as per our requirement. So for that we can easily have multi-range uh, uh, facility as well, in terms of the circuit diagrams represented in figure A and figure B. So these are two separate arrangements. Both of them will provide the facility of changing the ranges of measurement for the emitter. So if we discuss about the first type of multi-range emitter, so it is a simple arrangement, and the second type is a modified version that is called the Ayrton shunt arrangement. So in the first case, you can see that there are multiple shunt resistors available, and each of them are tuned in such a way that if the selector switch is located at a particular knob, then that particular range may be obtained for measurement. So IM and RM is supposed to be fixed for a particular PMMC. Now, depending upon the calculation for RSH shown in the previous slide, the values of R1 and R2 and R3 can be determined in order to enhance the range up to 10 ampere, 5 ampere, or 1 ampere. So if someone wants to measure from 0 to 100 ampere, then he can select this range, and accordingly for measuring up to 5 ampere currents, the second option could be selected, and in this way multiple shunt branches might be available, and tuning a selector switch to the particular knob, the different range selection can be done. Now another modified version of multi-range facility is or arrangement is shown in figure B, where you can see that the shunt resistances are connected in series. So three resistances R1, R2 and R3 are connected in series. So a sort of divider network is formed. So from each intersecting point a connection is taken. So the values are tuned in such a way that let's say if you place the selector switch at this 1 ampere point, then what will happen at this point, the summation of R1, R2 and R3 will be actually becoming the entire shunt resistance, or acting as the shunt resistance in case when the switch is located at 1 ampere. So I mean in that case, I mean what would be the total value of R1 and R2 and R3, the summation of these three, that can be determined like the way it was shown earlier. Now in order to determine the values of R1, R2 and R3, the process is not as simple as it is in case of the simple arrangement shown in figure A, because for this case, the Ayrton shunt arrangement, you have to what should I say, as there are three different resistances, you have to find three different equations Following the similar pattern of RSH that was shown in the previous slide, using a similar analysis, you have to form 3 unknown equations. And from those 3 unknown equations, you can solve the 3 unknown equations in order to determine R1, R2, and R3. Now, before discussing a little bit more about that, the possible advantage of this iron chant arrangement is that it overcomes the disadvantage that is inherent in this first type of arrangement. What is the disadvantage? Let's say the purpose of adding the shunt resistances is to protect the PMMC coil from receiving a high amount of currents, so that the current across the PMMC doesn't exceed its rated value or the full scale deflection value. Now, in case of switching from one point to another, so when the switching takes place, as the selector switch is moved from one shunt resistor to another, momentarily the shunt resistance is getting disconnected. I mean, during the period or during the moment when the switch location is changing, for that instant or small duration of time, there is no shunt resistance present in the circuit. So it might pass high current towards the PMMC coil, and momentarily, if receiving that high amount of current, may damage the PMMC coil. So that is one of the disadvantages of this sort of arrangement for multi-range emitter, which is omitted in the second type of arrangement. Because if you see this sort of an arrangement, the shunt resistance is always connected along with the PMMC. So changing the switch location from one point to another doesn't cause momentary disconnection of the shunt resistance, because the resistance is always there. Now, if the switch location is changing, even in that case, it is not this scenario is not going to appear that the PMMC is receiving high amount of current momentarily, I can say, or a small duration of time. So in using the second type of arrangement, the Ayrton shunt arrangement, better safety can be ensured for the PMMC coil. Now, if we discuss a little bit more about the Ayrton shunt arrangement, let's say when the switch is located at 1 ampere terminal. So at this point, we can write the equation for the shunt resistance to be, let's say, R1 plus R2 plus R3, which would equal to Rm divided by I by Im minus 1. So where I would be equal to 1 ampere and Im would be whatever the value is given for a particular PMMC, and the Rm, this value should also be fixed for a particular PMMC arrangement. Now when the switch is located at the second terminal, which is for 5 ampere, then what would be the equation for the shunt resistance? So the shunt resistance would be, in this case, R1 plus R2, and the other resistance R3 is now going to be added up with Rn. So it would be Rm plus R3 divided by I by Im minus 1. So this would be the, so let's say this is the first equation, this is the second equation. Similarly, for the third terminal, if the switch is located at third terminal, then the equation for the shunt resistance can be written as R1 equals Rm plus R2 plus R3 divided by I by Im minus 1. Okay, so for this case, the value of I is 1 ampere. For this case, it is 5 ampere. For this case, it is 10 ampere. So let's say these are the three equations. Now the three equations can be now solved simultaneously, and the values of R1, R2, and R3 can be determined. That is going to give the three values of the range selection using a fixed PMMC arrangement. So this is how the values of the resistances should be determined in case of iron shunt arrangement. Now, in order to talk about emitter sensitivity, so the sensitivity for this PMMC type emitters is determined normally by the amount of current that is required by the meter coil to produce full scale deflection of the pointer. So if the current required to produce the full scale deflection is represented by IFSD, then in a sense it can be said that the sensitivity would be inversely proportional to I by, it would be inversely proportional to the full scale deflection current. So the smaller the value of current required to give the full scale deflection current, the greater the sensitivity of the meter arrangement. So if there is a meter mechanism that requires 10 microampere current to produce full scale deflection, and there is another meter arrangement that requires 1 milliampere current to produce the full scale deflection, then as the first meter arrangement needs a less amount of current to give full scale deflection, or it can sense smaller amount of currents, then it can be said that the sensitivity of this type of meter arrangement is greater than the other one. So simply, the smaller the amount of full scale deflection current, the greater the sensitivity would be. Now, another aspect of using the emitters would be the phenomenon called meter loading, or the loading effect. That is, we all know that emitters are connected in series in order to measure current through a particular branch. Let's say for this simple mesh, we want to measure the current flowing through this particular mesh. So if we consider the circuit shown in figure A, our purpose would be to determine the current I, which would equal E divided by R. So that is the amount of current that we want to measure. Now, when we connect the ammeter in series, the resistance of the ammeter would get associated in the calculation. Let's say now instead of measuring I, we are measuring I1, which is E divided by R plus Rn. So the resistance of the meter arrangement also gets as added. Now here, I mean, this portion is actually indicating the ammeter, not only the PMMC. Okay, so this is the ammeter. Now here in the diagram, it is shown as the symbol of the, it is shown as a symbol of PMMC in terms of Rm and Im. But in general, I mean, as it is representing an ammeter, the effect of the shunt resistance would be also present over here. Now, if we don't consider the effect of the, I mean, shunt resistance, then we can say that the current that is going to flow through this particular mesh is going to be equal to Im1, or let's say the maximum amount of current that can be handled by the PMMC. Now in this case, as the resistance of PMMC is getting added in the calculation process. So the theoretical value of the current in the mesh that needs to be measured I, and what actually gets measured, that is IM1, is not going to be equal. So ideally the ratio, let's say IM1 by I should be equal, but in practical case this ratio doesn't remain equal to 1, rather it is less than 1, because IM1 is less than I. So it is necessary that the value of this resistance of the PMMC is kept as low as possible, so that it itself doesn't act as a load. Now adding the shunt resistance in forming the emitter also serves as a solution to this in lowering the effective value of the resistance or the equivalent resistance of the emitter, as the shunt resistance is connected in parallel, and the parallel combination of the shunt resistance and the PMMC would eventually result in a smaller valued resistance compared to both the individual values of RSH and RM. So in that way, adding the shunt resistance can lower the equivalent resistance of the emitter, and it can also minimize the loading effect. Moving on with the basic construction of DC voltmeter circuit. Now, using the same PMMC coil arrangement, DC voltmeter can also be constructed. And for this purpose, in order to measure voltages at higher ranges, instead of connecting resistance in parallel, a series resistor is connected. Let's say RS is connected in series to create a voltage divider network to divide the voltage so that the voltage across the PMMC doesn't exceed its rating. For example, let's say if a PMMC coil is designed to have a full scale deflection current of 50 microampere and an internal resistance of 1000 ohms, then the maximum amount of voltage that it can have across its terminals is Vm equals multiplication of these two terms. That would give actually 50 millivolts. So the voltage divider network has to be created in such a way that the voltage across the PMMC doesn't exceed this rated value, so that the coil of the PMMC doesn't get damaged. So keeping that in mind, the the resistance connected in series has to be, the value of that resistance has to be determined. So in this case, a KVL can be considered in this loop. So here, if we consider the KVL, we can write the input voltage to be equal to RSIM plus IM into RM. So from here, we can easily write the expression in this format to determine the value of the series resistance that needs to be connected in order to determine the range of input voltage that needs to be measured using this particular type of with the particular fixed specification of the PMMC. So IM, RM, these values are going to be fixed. Now, based on the limit of the maximum limit of the range of the input voltage, the value of the RS can be set accordingly. For voltmeters as well, multi-range arrangement can be done. And for voltmeters, the multi-range arrangement is done by connecting multiple resistances in series. So as these resistances normally increase the range of measurement, so these resistances are also referred to as multiplier resistors. So adding multiple multiplier resistances in series will in each intermediate stage increase the range of measurement as per the value of the resistance set by the manufacturer. So again, like the PMMC portion is going to have a fixed value of Im and Rn. Now first of all, here in order to determine the resistance required to give this 1 volt, give this range of 1 volt, that can be easily done by following the same process mentioned in the previous slide. That is V in by Im minus Rn. So here the value of V in should be set to 1 volts in order to determine the value of the resistance to measure voltage up to 1 volts. Im and Rm value should be set accordingly as specified for a particular PMMC. So once the value of R4 is determined, the value of R3 can also be determined. So for that, when the selector switch is located at R3, then what will happen? This the same equation can be used, but in this case, the two resistances R3 and summation of these two resistances should be considered. Later on, as the value of R4 is already determined in the previous stage, now the value of R3 now can be determined by taking the value of R4 on the right hand side for calculation purpose, and it can be written in this format. So using this second equation, the value of R3 can be determined, where the value of V in should be set to, it should be 10, and according to this diagram, it should be set to 10 volts, and all the other values should be used as per the mentioned data and the calculated data. So accordingly, the other series connected resistance for other ranges can also be determined, and multi-range facility for a voltmeter can be obtained. Now, in order to discuss the voltmeter sensitivity, the voltmeter sensitivity is normally defined in terms of ohms per volt. So if the voltmeter circuit is considered, the sensitivity, voltmeter sensitivity in terms of ohms per volt, it can be represented as Rn plus the series connected resistance divided by the input voltage. So now, although it is indicated with ohms per volts, but it is similarly related to the full scale deflection current as well as in case of the DC emitter, because ultimately the PMMC moving mechanism is used for constructing the voltmeter. So how much maximum current the PMMC coil can carry, that will actually give this measure of sensitivity for the voltmeter. So if V in is the maximum voltage, measured by voltmeter, then the full scale deflection current for the voltmeter can be easily written as V in divided by Rn plus Rs, considering the basic circuit shown in the one of the previous slides. So this is how the full-scale deflection current can be related in terms of voltmeters. So I mean, if that is the case, then this sensitivity equation, if the reciprocal of this term is taken, it can be also written as 1 divided by IFSD, or the inverse of the full-scale deflection current. So here in this case as well, the smaller the full-scale deflection current, the smaller changes can be detected by the PMMC, and the greater the sensitivity would be for a particular voltmeter arrangement. Now, for voltmeters, the loading effect also takes place considering the internal resistance of the voltmeters. Now, in case of voltmeters, as they are connected in parallel with the load across which the voltage needs to be measured, if the resistance of the voltmeter is too low compared to the load, then the voltmeter itself draws maximum or significant amount of current, or the major portion of the current flows through the voltmeter rather than flowing through the load itself. So in that sense, the voltmeter actually works as the main load, or it lowers the effective resistance of the circuit. I mean, the effective resistance between the load across which it is connected. So if the effective resistance is decreasing, the reading of the voltmeter will also change significantly. So this effect is normally referred to as the loading effect of the voltmeter. So I mean, to measure voltage drops across high resistances. Let's say if a high resistance branch is available, so in order to measure voltage using a voltmeter across that high resistance branch, so a voltmeter with high sensitivity should be used. So as the voltmeter sensitivity is normally defined in terms of ohms per volts, so a high sensitivity voltmeter means that the resistance of the voltmeter arrangement should be high as well. So if we discuss an example from the book of MMS Anand, the loading effect can be visualized a little bit better. So this circuit diagram is taken from example 1.6 of the MMS Anand book. So in this example, it is said that with a supply voltage of 75 volts, the voltage drop across the 25 kilo ohm resistance has to be measured. Now, two voltmeters are available. One is having 1 kilo ohm per volts sensitivity, and there is another voltmeter that is having a 20 kilo ohm per volts sensitivity. So two voltmeters are available. Now, in terms of these two voltmeters, which one is going to provide larger percentage of error, that can be determined, or in terms of percentage of error, the accuracy of the reading for these two voltmeters can be determined. Now, without doing the calculations, as per the loading effect is discussed, so you can easily suggest that the voltmeter with the higher sensitivity should give better performance, because the higher voltmeter which is having higher sensitivity, the resistance associated with that voltmeter is supposed to be getting supposed to be high as well. So less amount of current will be drawn by that particular voltmeter. So obviously the loading effect will be less for the high sensitivity voltmeter. Now in terms of the numerical values, now if we consider the theoretical calculation without considering the voltmeter connected across the across the 25K resistance, it can be said that the theoretical value for the voltage across 25 kilo ohm resistance here would be 25 volts if it is calculated theoretically. Now for the first case, considering the 1 kilo ohm per voltmeter, now for this, let's say we are using both the voltmeters. We are using both the voltmeters at 25 volt range. So the range of measurement for the voltmeters are set such that the voltmeters are capable of measuring up to 25 volts. So according to that, the value of RS is tuned. Let's say we assume that according to that, the value of RS is tuned. So a voltmeter that is having a 1 kilo ohm per volt sensitivity. So the voltmeter resistance, which is the summation of RS and Rn, would be one kilo ohm per volts multiplied by the range selected, which is 25 volts, and that would give us 25 kilo ohms. Now, so for the first case, we can consider that along with the 25 kilo ohm load, a voltmeter is connected that is having an internal resistance of 25 kilo ohms as well. So if this parallel combination of these two resistances are considered, and after that the voltage divider rule is applied, then the voltage across this voltmeter for case 1, I'm indicating it as V1, so it would give us 15 volts if we take the parallel combination of these two resistances and then apply the voltage divider between the 50 kilo ohm resistance and the parallel combination of these two equal resistances. So if it is 15 ohms, then for the first case, the percentage of error is 25 minus 15 by 25 to 100%, that is 40%. Now for the second case, if 20 kilo ohm per volt sensitivity of a voltmeter is used, which is also set at a range of 25 volts. For this case, the voltmeter resistance would be 20 kilo ohms per volts multiplied by 25. So in this case, the internal resistance of the voltmeter would be 500 kilo ohms. And using this value, so now let's say, along with the 25 kilo ohms load, if for the second case, a voltmeter is connected that is having a resistance of 500 kilo ohms. So in that case, again, if the parallel combination of these two resistances is taken, then finding the voltage drop across this node in terms of the voltage divider rule, it would be found that for this second case, the voltage across the voltmeter or this parallel branch, which is indicated by V2, would be 24.2 volts. So here the percentage of error decreases significantly, where the percentage of error is 3.2% only. So in this way, if a high sensitivity voltmeter is used, then the chances of loading effect or this impact of loading effect will be as minimum as possible. So You can later on again go through the example 1.6 in the book, and there is another example 1.7, so you can go through these examples. So they're straightforward calculations that indicate the significance or effect of the loading behavior of the voltmeters. So far we have been discussing about how the PMMC meter movement mechanism can be used to implement DC emitters or voltmeters. Now let us discuss about how the same PMMC meter movement mechanism that can be used in order to measure AC quantities, and in this case we are going to consider an half-wave rectifier based voltmeter first. So you can see that for this particular circuit arrangement of the half-wave rectifier based AC voltmeter, you can see it is similar to the one that was used in case of the DC voltmeter. The only modification is the insertion of this ideal diode, or this diode. So for analysis purpose, we are considering that the diode is going to work as an ideal diode. Now for this particular half-wave rectifier based meter, let's say a input source Vs is connected to the input terminals A and B of the voltmeter. Rs is the multiplying resistor of the voltmeter, and through the series diode it is connected with the PMMC coil. So for this half-wave rectifier based meter, the AC voltage source is going to have both the positive cycles and the negative cycles, but the presence of this diode will only pass the positive cycles towards the PMMC, we can say. So and the current wave shape will also become unidirectional in this case, where the negative cycles are going to be omitted from the negative cycles are going to be omitted, as the diode is supposed to become reverse biased in the negative cycle of the input voltage. So we are going to get only positive cycles of current flowing through the entire circuit. So the peak value of the supply voltage Vs is indicated over here as Vp. So in terms of the peak voltage, the peak value of the current can be easily written as Vp divided by Rn plus the multiplier resistor Rs. Now in this case, the deflection will converge, or the deflection will take place in terms of the average value of the rectified current. So the rectified wave shape we are getting over here. So in the positive cycles we are getting the current flow. In the negative cycle we are not getting any current flow. So overall the average current, let's say the average current will actually cause the overall deflection of the PMMC. So the deflection which is dependent on the average current. So the average current can be determined, the expression of the average current can be written as IAV equals, so we can integrate from 0 to pi, as within this division we are getting the change in current. So we can write it as sinusoidal as IP sine theta d theta. And in order to determine the average current, we can divide it by twice pi, because this pattern is repeating itself after every twice pi duration. So if we proceed with the integration, then we can take the peak value outside or factor out the peak value, because it is supposed to be fixed. Now later on, if we integrate, we will have minus cos theta from the limit 0 to pi. If we put the limit, ultimately the average value that we are going to get is going to be equal to ip divided by pi, and it can be further written as 0.318 into ip. So this expression for the average current can be considered for this case of half-wave rectifier based meter. So for AC voltmeters, the scale is calibrated in volts with the RMS value of the pure sinusoidal voltage considered. Okay, so if the RMS value is considered in case of the AC voltmeters, the RMS value, which is actually the peak value divided by root 2. So from here we can further elaborate the expression of the RMS value, represent the VP in terms of the current IP, and later on overall establishing a relation between the RMS value of the voltage and the multiplier resistor, so that we can get an expression of RS. So what should be the amount of RS that needs to be set in order to control the range of operation for the voltmeter. So here, instead of Vp, from this expression we can write it in terms of current multiplied by the resistances divided by root 2. So in the last slide, we have written up to this that Vrms equals Ip into Rm plus Rs divided by root 2, or we can say 0.707 into Ip into Rs plus Rm. Now Ip, we have a relation between Ip and the average current, that is over here. So we can replace Ip in terms of IAV. So if we do so, from here we can write it as 0.707 divided by 0.318 into I average into Rs plus Rm. Further, we can write it as 2.22 into I average into Rs plus Rm. And from here, we can write an expression for Rs, the multiplier resistor, which would be equal to 1 by 2.22 into Vrms by I average minus Rm. So eventually, finally, we'll get the expression for Rs to be equal to 0.45 Vrms divided by the average current minus Rm. So here, using this expression of the multiplier resistor, we can try to calculate the value of multiplier resistor in order to obtain a particular range of calculation. For instance, let's say the full-scale deflection current that the PMMC can handle is represented by IFST, and the maximum range of the input voltage that we want to determine is, let's say we can denote it as Vmax. So we can put these values of the full scale deflection current that can be handled by PMMC into this equation, and also the maximum range of operation that we want from or the maximum range of input voltage that we want to measure. We can put these two values into this equation instead of Vrms and IAV, and Rm is fixed for a particular coil. Then later on we can calculate what should be the required value of the multiplier resistor Rs to ensure that this amount of voltage can be measured using a particular PMMC coil. Now, moving on, let us discuss a few problems that is associated with this particular form of the circuit. So one of the problems is that in case of negative half cycle, as we are considering the diode to be operating as an ideal diode, we have considered the current to be 0 in the negative half cycle. Because the diode is reverse bias, it is forming an open circuit. But in practical scenario, the diode normally carries very small amount of reverse leakage current. So if that reverse leakage current, let's say if that reverse leakage current is considered, then the average value of the current will decrease. Okay, so from the calculation of the average current that was done in the previous expression, from that the value of the average current will decrease a little bit if the reverse leakage current is considered. So some modification can be done in the circuit diagram so that the effect of this reverse leakage current can be omitted. And also for the negative half cycle, if the magnitude of the negative voltage is very large, then the large reverse voltage may cause the diode to break down. And if the diode breaks down, if the reverse breakdown occurs, high amount of current will start flowing through the PMMC as well, which may damage the entire system. So in order to solve these two issues, the problems associated with the negative half cycle, another diode D2 is placed as shown in this particular diagram. So it is going to work sort of as a freewheeling diode. So during the negative half cycle, this second diode D2 will become forward bias and it will start conducting the current. So as this diode will start conducting the current, so the rest of the portion of the circuit starting from D1 up to the PMMC will be this will be disconnected from the flow of current during the negative half cycle. And for the negative half cycle, the current therefore will start flowing through the D2, shunting all the current through this forward biasing of D2, and through the PMMC movement mechanism there will be no current flow. Let us now discuss something about the sensitivity of this type of AC half-wave rectifier-based voltmeters. So for this type of modified version of the circuit, in the positive half cycle, the input resistance of the circuit can be considered to be equal to the summation of Rs and Rn, because in the positive half cycle, diode D1 is going to conduct, D2 is going to be reverse biased. So both the resistance will be present in the circuit. On the other hand, in the negative cycle, diode D2 will start conducting, D1 will remain reverse biased. So all the currents are going to flow through D2, as D2 is shunting the entire circuit. So in this case, in the negative half cycle, the input resistance to the circuit can be considered to be equal to Rs. Now, generally, the value of the shunt resistance, the multiplier resistance is very, very high compared to the internal resistance of the PMMC coil. So as the shunt resistance is very high, and also considering both the positive cycles and the negative cycles, overall, it can be said that our Rs can be considered as the overall internal resistance of the circuit in both the cycles. So if that is the case, then we can omit the effect of Rm from the equation of the multiplier resistor. So in one of the previous slides, we have written the expression of Rs. So considering both the cycles, as we are neglecting the effect of Rm, so we can rewrite this particular equation as this one shown over here. Now, before we determine, denote expression for sensitivity, we should consider the maximum current that can be handled by the PMMC, which is referred to as the full-scale deflection current. And we can assume that we are going to use that full-scale deflection current to indicate a particular amount of voltage or measure up to a particular amount of voltage. So that's why in the numerator also VFSD is indicated. So the full scale deflection voltage, or the maximum amount of voltage that we need to indicate using a particular meter. Now, as we are considering the Rs to be equal to the internal resistance of the circuit, we can rewrite it as Rin, as done over here. Now, considering the previous discussion regarding voltmeter sensitivity, which is defined as ohms per volts, so we can rearrange this this particular expression to signify the sensitivity. So the sensitivity is basically, for the voltmeter, the internal resistance of the circuit divided by the full scale deflection of the voltage, or the maximum voltage to be measured. So from here on, we can easily write the expression of the sensitivity to be 0.45 divided by IFSD. Now, if we compare it with the sensitivity of the DC voltmeter, in case of DC voltmeter, it was 1 divided by the full scale deflection current. So the sensitivity in case of this rectifier, half-wave rectifier based AC voltmeters, are decreasing. Almost it is even lower than the half of what we get in case of DC voltmeters, and which is also obvious because we are not getting a constant current supply to the PMMC. Rather, we are getting a rectified current at the PMMC, or through the PMMC. So if the average voltage is considered, if the average current is considered, then obviously the amount of current that we are losing, the negative half cycle that we are losing, we can, in that sense, we can say that the sensitivity is supposed to be a little bit less compared to the constant DC currents that we get in case of DC supply. Now, another problem about these half-wave rectifier based meters is the nonlinear behavior of the diodes in the lower RMS ranges, or the nonlinear behavior that the diode possesses in its characteristics. So normally we know the diode characteristics to be nonlinear as shown over here. Let's say I'm only showing the positive half cycle. So the nonlinearity is actually high in the lower ranges, or you can see the lower RMS ranges. After that, for higher values of the input voltage, the relation becomes sort of linear. So in order to keep the meter scale linear, it should be ensured that the diode D1 is operating in the linear region, which is, in higher RMS values of the input voltage, so that the diode is operating in the linear region, omitting the high nonlinearity in the lower ranges of the input voltage. So the shunt resistance RSH, in this case, a shunt resistance RSH can be added as a solution to this problem. So if the shunt resistance is added along with the voltmeter, or along with the PMMC, sorry. So along with the PMMC, if a shunt resistance is added, then the effect or equivalent resistance, or the parallel combination of these two resistances, will lower the equivalent resistance along this node. So the diode D1 can, if the resistance is decreasing, considering the parallel combination of both these resistances, if the resistance is equivalent resistance is decreasing, the diode D1 will be able to carry or draw more amount of current from the source. So if the current is increasing through the diode, then we can say that the diode would be operating in the higher ranges, that is almost linear. So if this shunt resistance is added, and let's say a scenario where RSH is equal to the internal resistance of the PMMC coil, then the current through D1 would actually double, or if it was previously indicated by I average, then now it would double, it would become IAV, twice IAV. So the expression of the multiplier resistance in this case can be further modified as 0.45 divided by Vrms. Now the current that is flowing through this diode is changing. So if this shunt resistance wasn't there, let's say IAV, this average amount of current would have been flowing through the diode. Now because of the presence of this shunt resistance RSH, let's say the amount of current is getting doubled. So here also in the expression of RS, we should introduce this multiplying factor of 2 in this case, minus, instead of only writing Rm, now we have to consider the parallel combination of RSH and Rm. So as there is a parallel combination of Rs and RSH, Rm and RSH, we should consider that. And along with that, to be more accurate in calculating the value of the multiplier resistor, we can also calculate the forward biasing resistance of the diode as well, or the forward resistance of the diode D1, which can be represented as RD, and adds that with the parallel combination of RSH and RM. So this would be the new or updated equation for calculating the multiplier resistor RS if this shunt branch is added, and also if the forward resistance of the diode is considered. So in this case, if this particular expression is considered, then the sensitivity of the half wave rectifier based meter for this arrangement of the circuit would be 0.45 divided by 2 into IFST. We can write in this pattern. So in this case, the sensitivity will further reduce. So in order to improve the accuracy, as modifications are done in the circuit diagram, the sensitivity is getting reduced a little bit compared to the initial case. Now here for this case, it was considered that let's say if RSH is equal to RM, then the value of the current will get doubled. But it might happen that RSH is having some other value which is not exactly equal to Rn. So in that case, the value of current, we should also update the value of the current accordingly. So for instance, in this case, let's say the current flowing through the diode is D1. The current flowing through the PMMC is IM. Current flowing through the shunt resistance is ISH. Now, if the shunt branch wasn't there, then the diode would actually carry the current IM, or we can say IAV. But if the shunt branch is present, then what will happen? Let's say the current that is going to flow through the PMMC, let's say IM, we have to rewrite it as, in case of current divider rule, we can write it as RSH divided by RSH plus RM into I, the current that is going to flow through the diode. So if these two values of the resistance RSH and RM are equal, then what we are going to have, then we are going to have a factor of 1 by 2 into I into IM. So from here we can write the current flowing through the diode to be 1 I equals twice into IM. So for rectifier based meters, we are actually indicating IM in terms of IAV, or average current, and that is being provided by the supply. So in that case, when both the resistances RSH and RM are equal, the value of the current is getting doubled. But if the values are not getting equal, let's say RSH is having a value of 200, RM is having a value of 50 ohms. So then accordingly, the multiplying factor along with the average current has to be determined. So for that case, what will happen? If we follow the same technique, it will have IM, or let me write I average equals 400 divided by, here I can write 450 into I. So the current that is going to flow through diode D1, it would actually be equal to 45 by 40 into IAV. So then that value of the current should be replaced into this equation. So for mathematical problems or analysis purpose, it has to be considered that whether these two resistances are equal or not. If they are equal, then it is straightforward that a multiplying factor for of 2 can be added with the average current. But if these resistances are not equal, then the multiplying factor will not be equal to 2, and it should be calculated accordingly before doing further analysis. Now, lastly, apart from the half-wave rectifier-based meter, full-wave rectifier-based meter can be considered as well. So here, the same PMMC meter movement mechanism can be used, and from the supply, if through a bridge rectifier, the rectified current I can be passed to the PMMC. So as a full bridge rectifier is used, the input voltage wave shape is going to be rectified, and a rectified current wave shape which is having both positive cycles for the positive half of the input voltage and also for the negative half of the input voltage. The positive peaks of the input current are supplied towards the PMMC. Now, in this case, a similar approach for analysis can be used, that is done in case of half-wave rectifier-based meter, to develop an expression for determining the suitable value of the multiplier resistor. Now, okay, in this figure, I think there should be a multiplier resistor shown over here, RS. So here the determination of the average value of the current would be a little bit different, because as we are getting positive peaks or positive half cycles of current for both the positive and negative half of the input supply. So here in this case, the average current can be determined as integration from 0 to pi IP sine theta into d theta. Now, as in this case, the positive half is repeating after each pi duration, or uh, after each pi radians. So we can divide by 1 by pi in this case, instead of dividing by 1 by twice pi, which was done in case of half-wave rectifier, because in case of half-wave rectifier, the positive cycles of the current was repeating after each twice pi radians. But in this case, after each pi radians, the half cycle of the current is repeating. So we can divide this integral part by 1 by pi in this case. And if we solve the integration similarly as we have done before, we would see that we are getting this sort of an expression, which can be further written as 0.636 into IP. So similarly, if we try to determine an expression for the multiplier resistor RS, we can follow the same process that was followed in case of half-wave rectifier. Now, in this case, just the multiplication factor will double. So instead of 0.45, as the average current is getting doubled, here as well, the multiplying factor will get doubled, and we can write the expression of multiplier resistor as 0.9 into Vrms by I average minus Rn. And similarly, if we consider the sensitivity of the full wave rectifier based meters, the sensitivity can be represented as 0.9 divided by the full scale deflection current. So for the full wave rectifier based meter, the sensitivity is also getting doubled compared to the half wave rectifier based meter. However, it is still less than the DC sensitivity, but it is better compared to the half-wave rectifier based meter. So up to these 4 this lecture. In the next lecture, the electrodynamic meter moment mechanism will be discussed, and after that we'll see some applications of the electrodynamic meter moment mechanism as well.